Greetings, pre-calculus students, to another day in our unit on the unit circle and trig. So today's lesson is basically a continuation of yesterday's lesson on solving trig equations, except today we're going to be looking at equations that are a little bit more complicated. Yesterday's equations were what one would call simple in the sense that you could basically solve them in one step. The equations that we're going to be looking at today are going to require more than one step to solve them. Okay, so the objective for today, I can use the unit circle to solve multi-step trigonometric equations without a calculator. Okay, so the equations that we're going to be looking at today will be solved without using a calculator, even though you can basically follow the exact same steps that we're going to be outlining today, even with problems where the values are not easily identifiable on the unit circle. So let's look at this first example. Okay. So get the trig equation by itself, then simply find the appropriate solutions using the unit circle, okay? So you want to get that trig term by itself, so the sine, cosine, tangent, whatever it is, and then you want to solve it like we just did yesterday. So here we have a hopefully simple example. Sine of x minus 1 is equal to 0, okay? So our goal is to get the sine of x by itself. Get the sine of x alone, okay? Or if it was cosine, tangent, whatever it may be, okay? So, just as you would any other normal algebraic equation, whenever you want to get a term by itself, you want to get rid of the terms around it, or you want to undo the terms around it so that you can move them to the other side. So in this case, since we want to get sine of x by itself, we want to get rid of that minus 1. Okay, and the way we undo minus 1 is we simply add 1 to both sides of the equation. So we end up with sine of x is equal to positive 1. And that's it. Now you would just solve this the same way we talked about it yesterday, which is since sine corresponds to the y value of the point on the unit circle, you want to look up when is y equal to 1 on the unit circle. And that just happens at pi over 2, assuming we're just looking at values between 0 and 2 pi. That is the only value on the unit circle where the y value is 1, or in other words, where the sine of x is equal to 1. So that would be your answer for that. Okay? So that's it. That's all you do. That's all you have to do. You just have to get the trig term by itself by adding, subtracting, multiplying, dividing, whatever you need to do in order to get it by itself. So let's look at one more example here before the rest you can try on your own. And let's look at this number 4 one. So we have square root of 3 times cosecant of theta, that's our variable this time, minus 1 equals 1. All right. So we have that minus 1, so let's get rid of that minus 1 first. All right, let's get rid of that minus 1 first. So we add 1 to both sides. So we end up with square root of 3 times cosecant of theta is equal to 2. Okay, that wasn't too bad. But we have another step here because we do have that square root of 3. We do have that square root of 3. So in order to get rid of that square root of 3, well, to undo multiplication, we divide. So we're going to divide both sides of this equation by the square root of 3. So we end up with cosecant of theta is equal to 2 over the square root of 3 because the square root of 3's cancel out on the left side. Okay, and now since this is cosecant, recall yesterday, whenever you're dealing with one of the reciprocal functions, you want to turn it into its corresponding function, which in this case would be sine, because now we can just flip this fraction and it's a lot more easier to figure out where sine is equal to square root of 3 over 2 as opposed to trying to figure out where cosecant is equal to 2 over square root of 3. Okay? So you look up the values on the unit circle and you would see that sine of theta is equal to square root of 3 over 2 at pi over 3 and 2 pi over 3. Okay? At those two radian measures, the point has a y value of square root of 3 over 2. All right, but I want you to pay attention to something here. And it's this. It says for all values. Well, what does that mean? Well, we kind of discussed this yesterday. Remember, the unit circle does go beyond 2 pi, right? There is 3 pi, there is 4 pi, there is 5 pi, there is 6 pi. The unit circle just keeps on going, right? You just have to keep on moving around and around and around the circle as much as you want. And we talked about this idea that in the unit circle, if you want to find additional values, you just add or subtract 2 pi to the answer that you ended up with. So if we wanted to find more answers, we would just add or subtract 2 pi to pi over 3 and 2 pi over 3. Well, what about if we wanted to generalize that? What if we were asked, what are all the solutions? Okay? Not just what are some of the solutions, what are all the solutions? Well, once again, if all you need to do to find additional solutions is add or subtract 2 pi, that means we can describe all the solutions. Okay, that means all the solutions are either pi over 3 plus 2 pi k. Okay, and you might be wondering, well, what in the world is k? K is just an integer, okay? So let me actually make a comment here off to the side. So k is some integer, okay? So k represents any integer. So an integer is any whole number, positive or negative. So 1, 2, 3, -1, -2, -3, so on and so forth. So we're basically saying here, as long as you have pi over 3 and you add any multiple of 2 pi, so 2 pi, 4 pi, 6 pi, or -2 pi, -4 pi, -6 pi, you will always get another solution, okay? So that's all that's saying, which would also mean that we can subsequently say that we also have 2 pi over 3 plus 2 pi k, okay? So whenever you want to describe all the solutions, so once again, whenever you're asked to determine for all values, that's when you have to make sure not only do you say pi over 3 or 2 pi over 3, but at that point you also have to say pi over 3 plus 2 pi k, 2 pi over 3 plus 2 pi k, because that encompasses all the solutions. Because at that point, you're just adding or subtracting 2 pi as many times as you want. Okay, so just be on the lookout, because as you can see, that happens for number 2. Okay, so the rest of the problems I want you to do on your own. So 1, 2, 3, and 4 I want you to do on your own. So not much more complicated than what you saw in number 4 for the rest of the problems here. Okay, so 1, 2, 3, and 4, 1, 2, 3, and 5, you can do on your own. All right, now let's look at the next example here. So solving when x or theta is not by itself. Okay, so solving when x or theta is not by itself. Okay, so you want to get the trig equation by itself, just like we did in the previous examples, and then you want to simply find the solutions using the unit circle, just like we did in the previous example, and then get x by itself. So let me show you what I mean. So we have this example here, sine of 2x, notice that 2 in front of the x, minus 1 is equal to 0. Okay, so once again, we want to get the sine by itself. Get the sine by itself, okay? Well, there's a minus 1 there. So in order to get sine by itself, we do have to undo that minus 1 by adding 1 to both sides of this equation. So we end up with sine of 2x is equal to 1. Okay, nothing too complicated there. Now we want to get rid of the sine. Well, how do you get rid of the sine? Well, this is where you got to look up the values. When is sine equal to 1? Okay, when is sine equal to 1? Well, we just did it in the previous example. Sine is equal to 1 at pi over 2. But notice something here. We don't have just x inside the parentheses anymore. We have 2x. So it's not that x is equal to pi over 2. It's 2x is equal to pi over 2 because that's what we have inside the parentheses, right? So once again, it's not x is equal to pi over 2 like we had in the previous example because it literally just was x inside the parentheses, but we have 2x is equal to pi over 2 because that's what's inside the parentheses. That's what's given to us this time around. So now we're not done yet. Now we have to get the x by itself because remember, you're solving for x. You're solving for the variable. So at this point, to get rid of the 2, you just divide both sides by 2. So x is equal to pi over 4. Okay, so pi over 2 divided by 2 is just pi over 4. So that would be your final answer. Okay, that would be your final answer. X is equal to pi over 4. Okay, so let's do one more example here. Which one was it that I wanted to try out? It was, I think it was number 10. Yeah. Let's do one more here. So number 10, let's look at number 10 because number 10 is a little bit more complicated. So here we have cosine, and inside the parentheses, we have theta over 2 plus pi over 3 is equal to 1. Okay, so that's what we have inside the parentheses. So you'll see here that the cosine is already by itself, right? It's not cosine minus 1. It's not 2 times cosine. No, it's just cosine. So cosine is by itself. So that part of our job has already been completed. So at this point, we can look up the values on the unit circle. When is cosine equal to 1? When is cosine equal to 1? Well, cosine is equal to 1 when x is equal to 1. So that happens at 0. Okay, that happens at 0. So 0, and if you want to say 2 pi, right, it also happens at 2 pi. So if you want to say 2 pi, you can do that too. Okay, but remember, look at what you have inside your parentheses. You don't just have a theta or you just have an x. You have theta over 2 plus pi over 3. So that is the equation you are now solving for. That is the equation you are now solving for. And you actually have two equations here. You have theta over 2 plus pi over 3 is equal to 0. And you have theta over 2 plus pi over 3, pi over 3 is equal to 2 pi. Because remember, we have two solutions. You're going to end up with two different equations here. All right, so for each of these, you're going to solve for theta. For each of these, you're going to solve for theta. So for the first one, or actually for both of these, to get rid of plus pi over 3, you subtract pi over 3. So let's quickly do that. So minus pi over 3, minus pi over 3. So we end up with theta over 2 is equal to negative pi over 3. And theta over 2 is equal to 5 pi over 3. We're not done yet though, because that theta variable is not by itself yet. It still has that over 2. So we got to cancel that out by multiplying both sides by 2. Okay? Multiplying both sides by 2, and the same thing happens on this equation because it's also theta over 2. So we end up with theta is equal to 2 pi over 3. Sorry, negative 2 pi over 3. And then this one ended up being, let's see. Excuse me. This one would end up being 10 pi over 3. Excuse me. 10 pi over 3. So those would be your solutions. But, and this is why I wanted to go over this one because it's a little bit more complicated, for all values. Remember what I just said in that a few problems ago. Whenever you're told to find the solution for all values, you got to make sure you put that plus 2 pi k at the end. And yes, you do have to specify where k is some integer. So you do have to specify that k is an integer because, right, k, we don't want k to be a fraction. No, we want k to be a whole number so that you can just add and subtract as many multiples of 2 pi as you want to get all the solutions. Okay, so that would be your final answer for that one. And obviously I wanted to go over number 10 because number 11 is going to be very similar, but you're going to try that on your own. Okay? Okay, so the rest, like I said, you can try on your own. So 6, 7, 8, 9, and 11 for this one. So 6, 7, 8, 9, 11, you can try on your own. And that is basically it for today's lesson. Okay? So solving trig equations that require more steps, but hopefully not too bad. Hopefully not too bad. I mean, 10 might have been a little bit tricky, but hopefully the rest won't be too much. But as usual, if something does cause an extreme amount of confusion, just let me know. Reach out to me as usual through the usual channels if you have any questions. But otherwise, I hope this lesson went smoothly. I hope you guys stay safe, and I hope you enjoy the rest of your days. See you later.